Hey chemists, in this video we're going to quickly follow up on more IR spectroscopy techniques and look at some subtle differences that we can explain when we look at very similar bonds in molecules that are ever so slightly different. We'll just start off by looking at another spectrum. Here's the spectrum of the vanillin compound, main component in vanilla, and has a very pleasant aroma as a result. Remember, IR spectroscopy shows us about differences of bonds. So we can see things like the carbonyl stretch, the CO double bond of the aldehyde at around 1700 or so. There's a uniquely very sharp OH stretch at the 3500 range of the vanillin molecule due to that OH bond right there. And then plenty of CH stretches in the 3000s, as well as some carbon-carbon double bond character in maybe the 1600s or so. And a reminder, this just tells us that those bonds are there. It does not tell us how they're put together, but if we suspect that this is the molecule, IR spectroscopy would certainly be a good way to confirm that those bonds are present and other bonds are not present. Now, sometimes the same bond in a molecule can show up differently, drastically differently, in an IR spectrum. And this can be due to resonance contribution that differentiates single versus double bond character. So I want to look at the carbonyl bond particularly and three different examples of carbonyl. These are all CO double bonds, and you can see that the carbonyl in this ketone shows up at 1716 wave numbers, which is an inverse centimeter, but the one in this enone shows up much lower, 1685, and then this cinnamaldehyde molecule is even lower, 1678. And the question simply says, use resonance contribution to explain this phenomenon, knowing that a longer bond will show up at a lower frequency. So not all of these carbon-oxygen bonds are created equally, and we can use resonance to explain this. So this is just a way to review some resonance principles and combining it with IR spectroscopy. Remember, one way to go about doing resonance is to look at dipoles. There's a significant dipole between the carbon and the oxygen toward the oxygen. So we could draw one resonance contributor for this ketone. That creates a separation of charge, but it shows some single bond character that's really always there for any carbon-oxygen double bond. The same thing can be done with the enone down below. I can draw a resonance contributor that shows that separation. Looks identical to what's above. However, in this example, there is another resonance contributor we can get by using this pi bond on the left. I still have charge separation, but now the positive charge is on this carbon in the lower left, as opposed to what used to be the carbonyl carbon. So this has more resonance contribution, and as a result, if we just look at the contributors that have a single bond associated with them, there's one in the first example, but there are two in the second example. This has more single bond character because of that resonance. And if there's more single bond, that means it's a longer bond. So this carbonyl is longer than the first one, resonance contribution. And as a result, it shows up at a lower stretch. So that is what explains exactly what we see. So to wrap up, I want you to hit pause and try and come up with as many different resonance contributions as you can for this aldehyde, and hopefully you'll see it explains why its stretch is even lower than the other two. Okay, so to start off, we're going to use the same contribution that we had in the previous two, where I simply delocalize that carbonyl pair of electrons up to the oxygen. And following that, we can actually mimic what the previous example did as well and walk that pi bond one over to the left. Remember, you only ever move pi bonds and lone pairs. In resonance, we don't break bonds. We don't move the atoms This is not even a different molecule. This is just a different way of us expressing where the electrons are shared unequally throughout this entire molecule. And because this carbocation that I've just created here is now benzylic, I have all the benzylic resonance contributors as well. So if I show them one at a time, benzylic is kind of like a hyperallylic state. We get all this extra contribution because it's one away from a benzene ring. This is really just an exercise at honing your resonance skills. That's why we're doing this. You'll notice, I hope so far, every contributor we've got has a carbon-oxygen single bond instead of the original carbon-oxygen double. So we are well onto our way with a longer bond. Now that the cation is in the ring, I can actually work it around the ring. That'll put a positive charge all the way on that carbon on the end there, and all the rest of this is still the same. So much of organic chemistry is recopying what you just drew and keeping it the same and only changing what's changed. I can work that cation around once more yet again. Snake it down here now. I always start by just copying what hasn't changed yet. And I go back and look what has changed. Now this pi bond is down here, so I will fill it in. And as a result, the plus charge is on the top carbon there. I can even go once more and put that pi bond back into the ring. This regenerates what looks like a benzene ring, gets that carbocation back to where it was a few contributors ago, but it technically still counts as a resonance contributor because it's ever so slightly different from the one that looks very similar. We've just shuffled pi bonds around in the 6-membered ring, so it does count as another contributor. And then I'll put a pair of brackets around this entire set of contributors. So this one has a lot of single bond character, lots of single bond CO character. And hence it is the lowest frequency. So for subtle different molecules like this, we can sometimes use this to explain the slight difference in location of where the signal shows up.